Welcome everyone to the session of Learning to Relight. My name is Zeshang Xu. I just graduated from UC San Diego with a PhD and will be starting as a research scientist at Adobe Research in a few weeks. I will first give an overview about neural rendering methods for relighting. Relighting a scene is essentially to first capture some images of the scene under some lighting conditions and then synthesize new images of the scene under novel lighting. So you want to keep the scene content unchanged and only change the lighting in the image. And one classical way to do this is, of course, to leverage some reconstruction. We can reconstruct the geometry and the reflectance of the scene from the captured images, and then we can naturally render the scene using the recovered components given any novel lighting. However, geometry reconstruction and reflectance reconstruction are both highly challenging problems, and it's very hard to avoid rendering artifacts. So another classical way of relighting is to avoid the explicit reconstruction and do image-based relighting. Here, the entire relighting process is abstracted as a black box function that encapsulates the geometry and reflectance in the entire light transport. The function is known as the light transport function, which can directly generate pixel values given any lighting conditions. So in general, we have two strategies for relighting. Image-based methods can generate photorealistic results. However, they require capturing a large number of images, which is very expensive, and they often focus on relighting from a fixed viewpoint. On the other hand, reconstruction methods leverage explicit geometry models, which naturally allow for changing the view, but the rendered images are usually less realistic. And recently, deep learning methods have been introduced to both types of methods, and the central idea is to replace the classical rendering module with novel neural rendering so that the acquisition can be easier and the results can be more realistic. So let's first talk about the image-based methods. Classically, this is done by capturing a lot of images under different lighting using a light stage. Then novel renderings under novel lighting can be directly generated by linearly combining these captured images. And this is the idea originally introduced in Paul Debrec's seminal relighting work. The results are actually very realistic, but they require hundreds and even thousands of input images. And the benefit of introducing deep learning here is that we can now leverage some data pairs to achieve the same output quality with significantly fewer input images. We explored this idea in our SIGGRAPH 2018 work. We showed that now you can capture a scene under just 5 directional light sources and use a deep neural network to relight it under any arbitrary directional lights. And you can further linearly combine these relight images to do relighting under complex environment maps. And in this work, we capture 5 images of the scene under 5 predefined lighting directions. Here, each gray dot represents a lighting direction, and the circle represents the upper hemisphere towards the camera, which is our lighting space. And we stack these images along with their lighting directions as the input to a deep neural network, and we call this network the RelightNet. It is an encoder-decoder style network, and the encoder reasons about the scene appearance from the inputs. We also take the novel lighting direction, process it with the network layers, and insert the feature into the bottleneck of the network. So the network decoder takes this feature and the scene encoding feature to infer the scene appearance under novel lighting and synthesize a relight image. We send different novel lighting directions to the network, and the RelightNet learns to synthesize the relight images correspondingly. Here, another important thing to note is that the quality of the relighting actually depends on the choice of input lighting directions. Therefore, we propose to let the network learn the lighting directions. And we start from a dense set of lighting directions and use a differentiable sampling network to sample the optimal set of sparse lighting directions. And these sparse lights are sent as input to the following RelightNet to relight. And the whole system is differentiable. We train the sample net and the RelightNet from end to end to minimize the relighting error, which jointly learns the optimal lighting directions and the relighting function. Our method can synthesize photorealistic relighting results on diverse real scenes from only 5 captured images. It well reproduces complex shading effects like challenging specularities and soft shadows. Our work introduces the first scene-independent relighting method, leveraging a network that can be generalized across different real scenes. Here, similar to classical image-based relighting, the view is always fixed. And later in our SIGGRAPH 2019 paper, we also show that this method can be combined with our view synthesis technique to do both view synthesis and relighting. We capture images under 6 lighting directions and 6 viewpoints. And then we can change the view very realistically using the view synthesis technique. And at any novel viewpoint, we can also stop and do the realistic relighting using the relighting technique I just introduced. Our relighting method is designed for relighting general real scenes, and it requires 5 or 6 images for high-quality results. Some recent works focus on category-specific relighting tasks and can do relighting with even fewer input images. They do human portrait or human body relighting with only 1 or 2 input images. Mek et al. Use a light stage to capture 2 images under color gradient lighting to achieve high-quality relighting. And you will get more details about this work later in the session. Some other works focus on relighting from a single image. And different from most previous methods that consider controlled known input lighting, these 3 methods relight a scene from a single image under unknown natural illumination. And these methods handle relighting and lighting estimation simultaneously. They leverage different lighting parameterizations and different training data to do realistic human relighting. And the central idea is still to use an encoder-decoder network to transform the input image to relate images. So far, I have briefly talked about neural rendering methods in image-based relighting. Essentially, these methods model the light transport functions as neural networks, enabling photorealistic results from just a few input images, and they improve the acquisition efficiency of image-based relighting. However, similar to traditional methods, these techniques still focus on fixed view cases. While they can be potentially combined with view synthesis techniques to support view changing, like what we have shown in our SIGGRAPH 2019 paper, these relighting techniques themselves are still designed for fixed viewpoint. To enable multi-view relighting, a more natural way is to consider some geometry information which is more relevant to the standard reconstruction-based relighting methods. And some recent work explores something related. They capture multi-view images around a scene and use multi-view stereo to reconstruct a mesh for their framework. And they apply neural networks to proceed the rendering, which synthesizes photorealistic results from the inaccurate reconstruction. In particular, Philip et al. Leveraged some rendering buffers and shadow maps for relighting, and you will get more information about this work later in the session. Chen et al. Optimized neural textures for the mesh and project the features to a novel view to do relighting. Here I'm summarizing the recent learning-based relighting methods. We can see that most of them are still purely image-based without considering any explicit geometry. And many of them use synthetic data for training, some recent ones leverage real data, and some work actually does per scene training and the network is not generalized across scenes. Lighting estimation has also been applied in many methods, allowing for relighting under uncontrolled natural illumination. In the end, I want to discuss some challenges and opportunities in this field. First, we can see that most works are still focused on fixed view relighting. Some work does consider geometry information for multi-view relighting, but the geometry is not learned but pre-computed from multi-view stereo. Meanwhile, there are also some view synthesis works that model the scene with neural representations without any mesh input. So a question is, can we do something similar for relighting? Secondly, current relighting works usually assume very simple lighting models. It's interesting to see if relighting can be combined with complex lighting models to produce more challenging shading effects. Finally, relighting usually assumes the scene content is unchanged. But can we actually make the scene editable and still properly relight it? This may require combining relighting more deeply with scene reconstruction methods. And in this CVPR, we have a reconstruction work in which we present a learning-based approach to reconstruct high-quality geometry and reflectance of real scenes from only 6 captured images, enabling both realistic relighting and view synthesis. In general, an interesting question is, how can we combine reconstruction techniques with neural rendering and make neural rendering with more flexible scene control? Thank you.
Hello everyone, my name is Julien Philippe. I'm a fourth year PhD student at Hagia Sophia Antipolis under the supervision of Dr. George Dretakis. And today I'll talk about multi-view relighting using a geometry-aware network. This is a joint work with Michael Garbi from Adobe Research, Tinkui Zhu, and Alexei Frost from UC Berkeley. First of all, what is relighting? Relighting is the fact of simulating your shot under novel and different lighting conditions. It's a re-rendering process. Here, we capture the scene under a single lighting condition and we're able to render this time-lapse effect video. If you're a photographer, you know that lighting is crucial to get a good-looking shot. Unfortunately, it often requires us to be at the right place at the right moment. And if you're just on vacation, your shot might look flat like this one. Thanks to our method, the user can interactively edit the lighting of the picture and get more dramatic effects, such as this one. So relighting is the fact of processing an input picture to get the same picture as if it was taken under different lighting conditions. There's been quite a lot of previous and related work in lighting estimation and image relighting. Some methods capture the same scene under several lighting conditions to build a basis that enable relighting. Some others focus on single-shot lighting estimation, which is convenient to insert new objects in a scene, but they do not edit the lighting of the pictures. Our work is also related to intrinsic images estimation, shadow detection, and shadow removal. Regarding relighting, there are methods that transfer lighting of a picture to another picture of the same place, or the picture of a sky to a given picture. Duchesne et al., which is the closest work to ours, use multi-view intrinsic images to enable relighting. In this work, we make the following assumptions. First, we focus on outdoor scenes. This enables us to use a simple lighting model, which is a directional light source, which is the sun, and a uniform sky. We assume that the user is providing a source and target sun direction, and we capture the scene under a single lighting. The main challenges of such an approach are the following. Given an input image, we need to be able to remove correctly the shadows and resynthesize them elsewhere, respecting the underlying geometry. Finally, we have to be able to change the global lighting of the picture, such as when the sun is going down. Given training pairs of images with input and target sun direction, we can train a network, our favorite one, let's say a UNet, to generate an output. Unfortunately, while doing that, shadows are poorly removed, and the network completely ignores the target direction, and shadows are not synthesized. This is because shadow synthesis is a very ill-posed problem. Given an input picture, several shapes can cast the same shadow. Here, we observe only the shadow of the palm tree, and the shape casting the shadow could be this one, or this one. And now when we want to move the sun direction, we have an infinity of candidates for the infinity of shapes that could have cast the shadow. So it's a very ill-posed problem, if we don't have geometry. That's why we introduce a geometry-aware relighting neural network. First, we get geometry from a multi-view input. Then, we use computer graphics to generate image space shadow buffers that are refined and then fed to a relighting network that is jointly trained on synthetic data. Our input is a multi-view dataset and a proxy geometry that we get from Structure for Motion and Multi-View Stereo. The user provides the source sun direction by clicking a point on the shadow and a point on the object casting the shadow. This proxy geometry already gives us cues for re-rendering and relighting. It gives us normal, camera orientation, surface, and depth, but that's not enough to carefully treat shadows that are crucial for outdoor scenes. Shadows appear when an object is occluding another with respect to a light source. In computer graphics, we know how to retrace shadow masks. We can cast ray towards the scene, then toward the light source, and get a yes or no answer for each pixel in the image to know if it's in the shadow or not. We get a binary shadow mask. This shadow mask is a natural candidate to help shadow removal. As you can see, shadow boundaries are roughly aligned with the one in the input image. But we can also compute this shadow mask for any given light source position. Thus, we can also compute it for the target sun direction and help shadow synthesis. Instead of just giving the input image and directions, we can now help the network with the source shadow mask and the target shadow mask. If we do that, we get some level of shadow removal and shadow synthesis, which was not the case before. But there are still a lot of artifacts, like this one, or the badly removed shadow here. The reason why we get those artifacts is that because the proxy geometry is very approximate. There are over reconstructions, inaccuracies, and a lot of noise. But when using only the geometry, we discard a lot of information in image space. For instance, if I texture this mesh, it's much easier to see the zones that were over reconstructed in the ceiling. That's why led us to introduce RGB shadow images. RGB shadow images are the RGB version of the shadow mask. But instead of just getting a yes or no answer, we grab the color of the object casting the shadow. Here it's a green. Here it's not in the shadow. Here it's brown. And for objects that are over reconstructed, such as this one, we will grab the background color. Here, the blue of the sky. As you can see, the RGB shadow image contains a much richer information than the black and white version. Here, we show this information on a real scene. As you can see on the right, the RGB version contains information that can help the network refine the shadow mask. If we directly replace the source and target shadow masks with our RGB shadow images, we already get an improvement in terms of quality. The synthesis is less rough than without the RGB version, but is still yet not perfect. That's why we introduce an intermediate refinement step that helps us get accurate binary shadow masks, which is what we wanted from the beginning. Here we show the result of our refinement network compared to the classical shadow masks. As you can see, our version is much more precise and overcome geometry issues. We just add this step of shadow refinement in between that we can supervise because we use synthetic data. We have two networks, one for source shadow refinement and one for target shadow refinement. This is because the two tasks are quite different. For the source, we need to be accurate to have a good shadow removal, and shadow edges are aligned more or less between the input and the output. While for target shadow refinement, we only need to be plausible, but we don't have as much information in the input image space. Finally, we can also compute from the geometry normal illumination layer and sun elevation that are good guide for global light changes. We input that to the network, and this is our final pipeline. How do we train our multi-stage network? In terms of data, we need pairs of images with different lighting. We need ground truth shadow mask for the intermediate supervision. We need geometry and multi-view datasets. The natural candidate is to use synthetic data. We render each viewpoint of 10 different synthetic scenes under 50 different lighting conditions. We can get the ground truth shadow mask thanks to the ground truth geometry, because we have perfect geometry. And we can do HDR renderings, which is very convenient for data augmentation and simulating different tone mapping operators. As I mentioned, we use synthetic data and we have perfect geometry, which is a big issue. This creates a domain gap. Thus, we use a dual representation of synthetic scenes by reconstructing a proxy geometry for the training scene. We compute our input buffers on this proxy geometry, while the rendering geometry is used to generate photorealistic images and supervision for the shadow masks. As you can see, there is quite a difference between the rendering geometry and the proxy one, which exhibit the same artifacts as MVS-like data that we use at test time. It's now time for some results. We show results for different input sources. First of all, cell phone pictures. Here, we show an interactive session with our method. As you can see, we can move shadows around, and the global color is adjusted with the position of the sun. This scene was captured in less than 5 minutes, and I took 100 pictures. We can also relight drone videos. Here, this is the input sequence. And this is a Relight version where we generated a time-lapse effect. We can also relight the output of image-based rendering algorithm, such as this unstructured lumigraph rendering. Here, it's an interactive session. Last, internet scale datasets. What if you went to south of France in this nice village and took a single picture? You cannot reconstruct the scene, but you can get picture from the internet to build your proxy and then use this proxy for our method and generate different Relight output of your picture. Here we compare an input with our result and the ground truth of a picture of the same place taken at a different time of day. Here are some more results where we dynamically modify the sun position. Let's talk about limitation and open the discussion. Our method heavily relies on the fact that the geometry is somehow accurate. Here, the geometry is completely broken, as you can see on this normal map of the same region. Thus, we cannot remove the shadow nor synthesize good-looking images. To recap, we use proxy geometry created from diverse multi-view sources, from which we compute RGB shadow images that are refined with subnetworks and fed to a relighting network that is trained on synthetic data for which we have a dual representation. I thank you for your attention.
All right. Good afternoon, folks. I hope you're all safe and healthy wherever you are. So, I have been tasked with a rather exciting challenge to talk about the latest developments in solving the neural inverse rendering problem. More particularly, I'll talk about techniques that take real world images or videos as input and disentangle the scene appearance into physical reflection components such as 3D geometry, surface reflectance, and the scene lighting. This is a crucial problem to solve for several forward rendering and compositing applications, such as retexturing, relighting, or novel view synthesis in AR or VR systems or in the movie and media industry. Let's begin by briefly introducing inverse rendering. So, we know that rendering is the process of taking a predefined 3D scene geometry along with its appearance parameters, such as reflectance and lighting, and generating a 2D image for a given camera view. Such a rendering is usually performed by ray tracing and solving what is called the rendering equation to estimate the radiance at a point of intersection of the ray with the scene geometry. Inverse rendering is the reverse process of estimating these 3D scene components from 2D images. As evident, this is a much more ambiguous problem with a lot more unknowns. The inverse rendering problem has traditionally suffered from three major issues. One is that acquiring ground truth scene reflectance or lighting requires complex equipment such as gonio-reflectometers or light stage and environment probes. And even these provide only sparse information in terms of sparse viewpoints and fixed position lighting and work only for static scenes. Second is that finding analytical representations for these physical parameters is challenging because these are high dimensional and high frequency functions. And third, the interaction between these components is quite complex, which leads to a very dense system of nonlinear equations that often require iterative optimizers that need multiple update loops over several variables, making it computationally intractable. And even when solved, the globally optimal solution is often elusive. So, the good news is that recent developments in deep learning have allowed us to learn data driven implicit neural representations for this task that makes unsupervised or self supervised learning possible, even from unstructured and uncalibrated input images to various degrees. This has led to several exciting breakthroughs in this area recently. I'll try to offer a selection in this talk that hopefully touch on some of the major new ideas and developments. One of the simplest forms of inverse rendering problem is that of intrinsic image decomposition. Such a decomposition can be arrived at by making simplifying assumptions about the scene. Given the rendering equation, if we assume that the scene reflectance is Lambertian, that is, the surfaces reflect light equally in all directions, the image can be decomposed into two intrinsic layers of albedo and shading. This is a classic computer vision problem, but recently learning of data driven priors has pushed the state of the art significantly. Let me talk about four interesting categories of approaches that I see in recent works. One of the classical datasets for intrinsic decomposition has been the intrinsic images in the wild dataset by Bell and colleagues. This provided manually annotated ordinal relationship between image patches based on their underlying reflectance brightness. This work by Zhao and colleagues is trained on this dataset to predict relative reflectance ordering between image patches, which is then used in an energy minimization framework to solve the decomposition. They show that using this technique, they're able to learn feature embeddings that can classify various material classes, such as bathroom tiles, wallpapers, and cloth surfaces, without ever being given these ground truth labels. Interestingly, another category of work builds in this direction of learning discriminative feature encodings from synthetic data. This approach from Wang and Lu learns the distinctive characteristics between different intrinsic components in a high dimensional feature embedding space using synthetic training pairs. The latest approach by Liu and colleagues that we'll see in this conference takes this a step ahead by learning the latent features in a completely unsupervised fashion from a collection of uncorrelated training images. This is done by casting intrinsic decomposition as a domain translation problem, which I think is pretty neat. Another interesting direction that we see quite a lot of work come out is using time lapse images to learn to perform intrinsic decomposition. Using sequences of a scene where the lighting is varying but the reflectance is constant has been exploited for additional constraint and classical approaches as well. These techniques use a shared weight network to estimate the decomposition across various frames of the sequence and apply a cross reconstruction loss, which imposes a constraint that the estimated albedo images should be constant across the sequence. A similar dataset that has been exploited for learning intrinsic decomposition is crowdsourced multi-view images of outdoor structures and monuments. This work by Ewan Smith explores such a dataset to first perform a multi-view stereo reconstruction of the monument and then uses the correspondence across the views to impose a similar reflectance consistency constraint across the views. They're able to use the accurate geometry along with the reconstruction laws to learn to perform real-time intrinsic decomposition even for video streams. But intrinsic decomposition is a very limiting version of the inverse rendering problem because it does not attempt to estimate the scene geometry and makes a very simplifying assumption about the scene reflectance. While this works for applications such as retexturing or recoloring, performing relighting and novel view synthesis requires 3D geometry and non-Lambertian reflectance. We've recently seen a lot of work in estimating spatially varying BRDF of planar samples. These several methods take as input a single image of a planar material sample captured under flash lighting. This provides a shadow-free image with specular highlights from a point light source. Using ground truth labels from artistically generated or procedurally generated material samples with ground truth data, the methods employ a neural network to learn to estimate parametric reflectance components of diffuse and specular albedo maps and roughness map of the material. Similar to the intrinsic decomposition problem, several of the newer methods employ multiple images to perform an even better quality of parametric reflectance estimation for planar objects by using more samples in the light view direction space, as seen in the image on the left. On the right, you see a comparison of the relighting using the estimated parameters from previous single image methods and the new multiple input image-based method. While these methods have pushed the state of the art and are very useful for quick reflectance acquisition for fabrics and metals which are near planar, they do not generalize to 3D objects. More recently, we see another host of methods that use multi-view imagery of a 3D object to estimate its geometry and reflectance. This method by Meka and colleagues employs a rendering process-based neural pipeline to input an RGBD video stream and estimate intrinsic images, high-frequency environmental lighting, and parametric reflectance for an object of constant material and arbitrary shapes, and all of that in real time. This allows for interesting applications such as photorealistic rendering of virtual objects made of material taken from real objects. More recently, no-flash imagery has been extended to estimate spatially varying BRDF and 3D geometry of objects. A co-located camera and light source allows for acquiring images of the object under known lighting conditions, which can be used to estimate the geometry and reflectance maps. In this conference, we will see further an extension of using co-located camera and light sources in a sparse multi-view setup with as few as 6 images to estimate even more accurate geometry and reflectance maps of specular objects of arbitrary unknown shapes. One of the most exciting developments in this area has been the development of differentiable ray tracers. These are ray tracers that can provide the derivative of the scene radiance with respect to scene parameters such as material and lighting. Such a differentiable block can be used to provide reconstruction losses to neural networks and backprop through them, and given the right constraints, accurately estimate the combination of scene parameters that result in the image. Such differentiable ray tracers are perfect tools for inverse rendering tasks. On the left, you see such a differential renderer at play and how over several iterations, the improved quality of the scene parameters leads to better reconstruction of the scene image. On the right, you see a differentiable Monte Carlo renderer applied to estimating scene reflectance and light transport. This leads to realistic virtual object insertion into the scene. Although this method uses perfect ground truth geometry from synthetic scenes as input, we can hope to see the geometry being jointly estimated in future works. Alright, now I'd like to talk about solving the inverse rendering problem for an interesting class of objects, human faces. This is a very interesting problem because human skin is a complex material and photorealistically modeling its appearance is difficult. Recently, we've seen very interesting work that uses unsupervised learning by fitting a 3D face model to in-the-wild images. This work by Tiwari and colleagues uses a handcrafted differentiable renderer for the 3D face model to estimate the parameters of a given human face image. More interestingly, they extend this work for videos or multi-view images of the face of the same person while simultaneously learning mesh deformation over the 3D face model. This allows the network to also model difficult facial features such as facial hair. While these models do a great job of estimating coarse geometry and albedo, they're not able to capture the high-frequency texture and reflectance effects. Another interesting piece of work uses high-quality data acquired from a light stage to learn to estimate such high-frequency effects. This method also learns to estimate the parameters of a base 3D model, but also estimates high-frequency displacement maps and reflectance textures on top of it. Such a model can then be run at test time on single in the wild images to estimate a relightable 3D model. While the method achieves state-of-the-art results for face skin, it is not able to model facial hair, eyes, etc. More recently, we have used the light stage to acquire very high quality facial reflectance fields using a particular lighting condition known as the color gradient elimination. The human skin has complex reflectance which is difficult to model analytically. This method circumvents that problem by estimating a full reflectance basis for the face from just these two images. I'll go into a little bit more detail about this work. So let me first briefly introduce the light stage. A light stage is a studio device consisting of calibrated lights and cameras that cover a capture volume. The way the light stage works is it captures multi-view images of a person in a static pose by switching on one light at a time. While this technique is great for capturing a static face, obviously capturing such OLED data for video or of a facial performance is impossible because we cannot switch through all the lights of the light stage at a fast enough rate for each frame of the video. One solution to this problem was proposed by Fife and colleagues back in SIGGRAPH 2009, where they showed that color gradient elimination is a lighting pattern under which only two images need to be captured, such that the full reflectance field of the face can be extracted from it. The color gradient elimination is a lighting pattern in which the RGB channels of the lights linearly change across the XYZ coordinates of the light position. But this work relied on a very simplistic reflectance model called the cosine lobe reflectance. But such a simple model cannot replicate many intricate light transport effects, such as shadow, subsurface scattering, and global illumination. Using deep learning, we developed a novel method to learn to extract the full OLED reflectance field, including all light transport effects of every frame of a facial performance of video in a light stage captured under such color gradient elimination. This overall setup poses many interesting challenges. Let's look at them one by one. Since we are working with very high resolution and large data set, the dimensionality of our input-output is huge and as such intractable. The training data consists of only a small number of subjects that can be scanned, but at test time we need it to work for people of arbitrary identities. With such a small training domain, generalization across identity is a big challenge. The training pairs are captured by asking the person to stay still for several seconds, but there is a small amount of unavoidable subject motion which results in misregistration between input-output pairs. This problem becomes even more obvious due to the high-resolution 4K images. This can lead to very blurred results. Since the goal is to obtain high-quality output which is faithful up to individual pores and hairs on the face, this is a major challenge. Facial reflectance exhibits spatially vastly changing high-frequency reflectance effects such as specularities. While these specularities may not cause a lot of pixel error, they are very perceivable by humans. Thus, it is important to capture these high-frequency effects for high-fidelity reconstructions. We propose a novel formulation that addresses all these challenges and generates high-quality, high-resolution reflectance fields. So instead of reflectance regression, the problem is formulated as a local reflectance modeling in 2D reflectance space. A fully convolutional unit is trained to model the reflectance field. Each training sample is formulated as a single sample point in the 2D reflectance function for a small local spatial region of the face. So we generate random crops of the input-output pairs. We concatenate to every pixel in the input image a 3D vector that is the lighting direction of the light corresponding to an OLED, and train the network to regress the corresponding crop of the OLED image. This formulation affords us several advantages. To solve the problem of intractable dimensionality of the problem that we are trying to solve by training the unit neural network to be a reflectance function approximator. Secondly, since the network learns the reflectance function by looking at only local crops of the face, it is able to not overfit to facial identities it is trained and instead generalize for any new identity. Now let me show you how this formulation allows us to solve the third challenge of misregistration of input-output pairs. The motion of the human head in this context would be a 3D transformation consisting of translation, rotation, and also some nonlinear deformation. But since we are working with only small spatial crops, the misregistration can be approximated simply as a local translation. For example, in this training pair, it can be seen that due to misregistration, the output OLED image appears to be translated to the top left. We run the input gradient images through the network, and instead of computing the loss on the corresponding crop position in the ground truth, we search in a locally translated neighborhood the crop that gives the least error. Of course, this will not provide a completely accurate correspondence between the input output pairs, but in our experience, this is sufficient to reduce the misregistration error to a point that the network does not blur out the skin details. Finally, let us look at the loss function to solve the fourth challenge. In order to preserve the high frequency details of the human face texture, such as pores and individual hairs, the widely used VGG16 based perception loss is used. This is imposed by having an L2 loss on the feature activations of the various convolution layers of the VGG16 network trained on the ImageNet classification task. While this works really well to preserve the high frequency diffuse texture, in our observation, this does not work well in preserving the high frequency specularities. In order to preserve specularities, a novel task dependent loss is used. For this, a VGG16 network is trained on a novel task of looking at very small crops of the ground truth OLAT image and regressing the lighting direction corresponding to the OLAT image. This is a useful task in this case because the network learns to extract those features of the OLAT image which inform about the lighting direction, particularly the specularities and shadows. Now, the features of this new VGG network are sensitive to image features corresponding to the specularities. The OLAT prediction and the ground truth OLAT are fed to the VGG network, and an L2 loss is imposed on the difference between the feature activations. And that solves the fourth challenge. Now, let's look at some results. Since the unit is a fully convolution network, even though we've trained on small crops during training, at inference time, the network runs on full gradient images of the face. Here you see two color gradient images that are the input, and you can see three high quality OLAT images regressed as compared to the ground truth. You can notice that the network regresses very accurate shading and shadows around the face. Notice the accurate position of the specularities on the eye. Here is a video of an actor doing some facial performances from two specific lighting directions. As you can note, such videos can never really be captured in a real light stage because you can only relight from one direction at a time. Relighting such dynamic performances at such high quality is made possible for the very first time. Since publishing this work, we have extended the training data for full human body. The network can now generalize to any arbitrary person inside the light stage and estimate the full reflectance field for any viewpoint given the two gradient images. In other talks in this tutorial, you will see more of our future work where we extend this approach to also generate free viewpoint relightable performances of dynamic full human body performances with complex hair and clothing. All right, with that, I'll end this talk. Thank you.
Hello, everyone. I'm Sean Fanello from Google, and I'm going to talk about neural rendering for performance capture. For those that are not familiar with what performance capture is, it is also known as free viewpoint videos or volumetric capture or volumetric videos. And the goal is usually to have a performer captured from multiple viewpoints with high resolution RGB images and custom depth sensors. And you probably want to recover a 3D model of the subject and perhaps also retrieve reflectance properties such as surface normals, gloss maps, and albedo. And then you can take these 3D models and render them in real and virtual scenes and make them look like they're really composited there. Here we're seeing some examples of our relightable system. You see that the reconstructions look pretty compelling and appealing. However, if you're an expert eye, you could tell that something is off, especially in those areas with complex structures such as hair, or view-dependent effects and specular highlights are actually completely missing. These look pretty diffuse overall. Now, why is performance capture important? Well, performance capture, if you're working in this field, can be used to generate a lot of 3D content for mixed reality applications, such as virtual and augmented reality, as shown in these examples here. But also, if you can rely on real-time performance capture, you can take one subject, reconstruct it in one place, and then stream it to another place. And you can start having these very compelling scenarios with real-time telepresence systems where two subjects that are located in different parts of the world, they can actually communicate and interact like if they're physically in the same place. As example here, we showed the holoportation back in 2016, and these days there are even better, higher quality works that rely on neural rendering. Another application, which is perhaps less obvious, is actually how to use these complicated systems to generate ground truth data for machine learning. If you're a machine learning person, you probably are spending 80% of your time cleaning up your data and making sure that your inputs and outputs are actually matching and the ground truth is actually ground truth, right? If you have these systems, you can imagine you can take these pretty accurate 3D models. You can start applying triangulation on key points and retrieve triangulated, temporally consistent body pose key points, hand tracking, face tracking, and you can use them to train systems in the wild. Similar for depth estimation tasks. You can use these systems to generate ground truth depth from single RGB images, but also people segmentation and mapping and relighting and compositing. If you look at all these tasks, they all have something in common, which is photorealism. They all rely on high quality renderings, photorealistic renderings to actually train machine learning models. So why is it so hard to capture and render photorealistic humans? Let's take a look at the state-of-art pipeline. In this case, we're going to talk about the Relightables pipeline, but many of the things that I'm going to tell you, they're actually shared among many volumetric capture pipelines. All of them, they usually start from 2D images and perhaps custom depth sensors. And the goal is from these 2D images, you want to build a 3D model, a 3D representation of your subject. You usually want also to parameterize these 3D models to have a common texture space where you can blend together all the multi-view images in this common texture space. Then if you assume a certain BRDF model, and perhaps you can rely on complementary illumination conditions, such as the ones we use for the relightables, you can start inferring surface properties such as albedo, gloss maps, and surface normals. And finally, given a 3D model with reflectance properties, you can render it with any desired illumination condition and from any desired camera position. So what are the problems with these pipelines? There are actually a few. No matter how accurate and precise your reconstruction is, a 3D mesh is not expressive enough to capture high frequency details and complex structures such as individual hair strands, for instance, right? That's pretty complicated. or also transparent objects and translucent objects. Then you usually have some imperfections in your geometry and calibration that cannot be avoided. And when you start blending all these multiple viewpoints into this single texture map, what you get is usually results that are not as sharp as the input images, and you start to observe some blurry results. Then most of these works, including the relightables, rely on a handcrafted BRDF model, for instance, a Phong model, or in the relightables we used a cosine model. So you're already giving up some material properties there. And finally, once you have this 3D model, you still need to perform a certain rendering phase. And the rendering phase is very challenging, and usually people approximate it, or there are a lot of post-processing steps, such as the ones that artists rely on in Hollywood productions. Even if we assume for a second that we have a perfect geometry and a perfect reflectance model, imagine you have the best system in the world, you can capture perfect geometry and perfect reflectance properties. We still need to solve the rendering equation. And when we start adding high-order light transport effects, such as global illumination, intra-reflection, subsurface scattering, you see that actually solving this rendering equation is not that simple. And the geometry and the BRDF plays just one part of the rendering equation, and you still need to approximate it. So how do we actually solve it? Well, we can use neural rendering to learn all these high-order light transport effects directly from the data without having to model them directly. But how do we apply neural rendering in practice? What is the right representation? There are many available, actually. Some methods rely on a base geometry and then apply neural rendering on top. Others trying to learn directly a volume and a 3D representation directly from the images. We're going to see more details later. Rohit and Steven are going to talk about both these classes of methods. There isn't the right answer here. Each of these methods has pros and cons, and usually depends on the actual application that you're trying to solve. In this talk, we're going to take a brief look at those methods that rely on geometry, on a certain geometry acquired by this system. And the reason is because they actually played very well with these pipelines that I described earlier. Indeed, if we take a traditional computer graphics and computer vision volumetric capture pipeline, you can apply neural rendering pretty much everywhere you want. For instance, in the Looking Good work that we presented a couple of years ago, what we did was to apply neural rendering at the very, very end. So you have a 3D model acquired with whatever system you like. You render this model using any sort of approximations you want, any sort of handcrafted BRDF. But then you have a neural re-rendering phase where you take the rendered image, and this neural rendering tries to retrieve the final photorealism. So it's more an image-to-image translation task rather than an actual rendering phase, where the neural re-rendering is trying to recover the photorealism. Another approach presented by Eustace T.S. et al. Is different neural textures, which also plays very well in this sort of pipelines. Instead of storing RGB values in your texture space, in your parameterized texture space, what you do is at training time, you actually backpropagate through the texture, and you learn neural features such that at test time, you can resample this texture to an image space, and then you're going to have a neural rendering module that is able to decode these learned representations and giving you the final rendering results as shown here. But does neural rendering actually work? Let's take a look at this example. On the left, you have the output of the Relightables pipeline after performing HDRI relighting in this environment. And on the right, you have the same but with neural rendering. You'll see that in this particular example with a very strong illumination condition, you see that neural rendering is actually able to model those high-order light transport effects such as view-dependent effects and specular highlights that computer graphics pipeline doesn't really capture that well. It's still not perfect, but it's definitely an improvement in terms of photorealism. So are we done with performance capture using neural rendering? Well, no. The majority of these methods suffer from limitations. Many of them don't even generalize to unseen subjects, and you need to retrain a machine learning model even per frame if the parameterization changes. The majority of them doesn't support relightability, and some of them cannot really account for free viewpoint videos, but usually have a fixed scale, or they can support a half hemisphere. But more importantly, all these methods, they usually rely on this pretty complex capture system with multiple cameras. And our goal is really to scale performance capture system to just a single RGB sensor. All right, that was pretty much it in terms of the overview for performance capture when you are rendering. Now we're gonna have Rohit and Steven that are gonna talk about the details, the algorithmic details for these approaches. Thank you.
Hello everyone, I'm Rohit Pandey, and I'll be presenting some of the work that we've been doing around neural rendering for dynamic performance capture at the Augmented Perception Group at Google. So a brief outline of this talk is that I'm going to go over neural rendering for people and what's already been done and how we want to extend this work. I'll briefly mention some details of Looking Good, a work we had at SIGGRAPH Asia 2018, some details of Simply Looking Good, also known as volumetric capture of humans with a single RGBD camera via semi-parametric learning, which was published at CVPR 2019. And then I'll get into how we extended Looking Good with better data and adding new controllable parameters to it, like relighting. And finally, why our latest work, Deep Relightable Textures, also known as Deep Relightables, which is the first work that looks at controlling, synthesizing new viewpoints and new lighting conditions while supporting people under motion and generalizing to unseen people. And finally, I'll tease some of the in-the-wild applications of using neural render data as ground truth, as Sean mentioned in the previous talk. So an overview of neural rendering for people. This is an excerpt from our state-of-the-art on neural rendering star report at Eurographics. And this is a subset which deals with the contents as people. So if you look at the controllable parameters, there's C for cameras and C and P, which is for pose. There are also, of course, a lot of work that deal with lighting synthesis only, but I would like to point out that not a lot of works deal with camera and lighting synthesis while supporting people under motion and while supporting generalization to unseen people. So coming to Looking Good, it's a fairly straightforward approach, actually. We had a mesh which had a lot of shortcomings due to it coming from a real-time reconstruction pipeline. And we rendered this mesh and we got a lower quality rendering, which had certain issues like low quality texture, it had certain holes, bad boundaries. And what we thought was, hey, let's re-render this mesh using a deep architecture to a better version of it. The way we supervise the better version is by adding additional witness cameras into our rig, which were of potentially higher quality and resolution than the cameras that were used for constructing this mesh. So that was the general idea. There was a rendered input, which was in the target view itself. Then we used the UNet-like architecture to output RGB and mask. The RGB was supervised by the ground truth masked RGB from the witness cameras. And the mask was supervised with this binarized semantic mask. The actual semantic labels were used for additional things like adding additional loss to the head, for example. So as I mentioned, the network architecture was super simple. It was a UNet, but the crux of making an approach like Looking Good work lay in the losses. We had to use some carefully handcrafted losses to make this approach work, not because the approach or the problem was inherently hard, but because our data was inherently hard. We had noisy masks. We had really low quality meshes as input. So we needed all these additional losses. And I would refer you to the paper for details of each one of these. The saliency loss was a little interesting. As you see on the image on the right, without the saliency loss, the network mostly concentrated on the boundary where the mask was noisy. And with the saliency loss, it actually concentrated on the person a bit more. So let's look at some results really quick. If you look at the input and the prediction, The input is greatly improved, I would say. The resolution improves, all the holes are filled. This is for seen people, of course. There's some issues still remaining around the edges and with some temporal stability. Moving to unseen people, you'll notice that the generalization of the colors is mostly okay. Where it struggled was to synthesize geometry that did not exist in the input for an unseen person. For example, my hair over here looks like a completely different person. The ears were in fact interesting. It fixes the ear, although it might give the person a ear that was not really theirs, but looked realistic to the network. Similarly, we have some results on the single camera scenario where you'll notice that the textures are sharper because it was a single camera and there was no fusion, but since it was a single camera, the network had to hole fill a lot more. It does a decent job even with our weak temporal term. We got results that were fairly believable. As for unseen people, we see that the results are fairly similar to the seen person case, the same advantages, but of course the whole thing suffers a tiny bit. Now, I quickly wanted to draw attention to Simply Looking Good, a work that was published at CVPR 2019, also called Volumetric Capture of Humans with a Single RGBD Camera via Semi-Parametric Learning. Here, we worked in a slightly tangential direction, which was along the direction of dropping infrastructure. How did we want to do this? Like, how did we want to make volumetric capture more accessible to users at home? We wanted to reduce the multi-view setup to a single camera. The problem with this is that when you have a single camera, you can, of course, not see things that single camera did not see. Like, for example, when you're looking at the front, you cannot see the back of the person. If you're looking at the back of the person, you cannot see the front of the person. So the general idea was we can use a previously seen set of calibration images to infer the parts that you cannot see in the current view. This could be in the form of the person coming in front of the system and turning around once in any arbitrary pose. The system was robust to that. And then we at least had information about the parts that we could not see in future views. So here's the basic idea again. From the back view, in the extreme case, we wanted to synthesize all these views, and we wanted to see whether this was possible. And indeed, it was possible. One of these is actually a predicted view. And I would refer you to the paper for more details on this. There were some issues with temporal stability, but basically we wanted to make sure, we wanted to know whether such an approach would be credible at all. And it was, even though it was a very difficult problem. Now, the two approaches that I mentioned were trained on the same data set. This was coming from our older rig. This rig had 1 megapixel cameras. It had about 8 cameras, and the data set only had about 15 subjects. And the reconstruction methods that we used for the mesh for Looking Good, for example, came from a real-time reconstruction method, Motion to Fusion Duo et al. 2017 in this case. Now, we realized that a lot of the shortcomings of our results were because of the data that we were capturing. So we went and built a better rig. This rig had 12 megapixel camera resolution. It had 60 cameras, and we went and collected a bigger data set of about 70 people. And we used an offline reconstruction method, the Relightables from Gu et al. 2019, which had much higher quality. So what does this earn us? If you look at the mesh difference, it's quite huge. The old mesh on the left of Christoph and the new mesh in the center. And the old mesh arguably does not even look like Christoph anymore. The huge holes, the texture resolution is very low quality. The new mesh looks much better and differs from the ground truth shown on the right only in view-dependent effects, I would say, because there's still some texture merging happening here. Of course, the mask could be better, but arguably you could say that going from the new mesh to the ground truth is a lot simpler for an approach like Looking Good. In fact, that's what we tried next. We tried running Looking Good on the new meshes. Note that the mesh that I just showed in the slide before has baked-in lighting. And this works. But of course, relighting was not possible. And the direction we wanted to move in was to extend Looking Good towards relighting. How do you add relighting to an approach like Looking Good? We required meshes that were rendered in the target lighting condition. Now, these need to come from gradient images in order to support dynamic capture. A one light at a time sequence requires the subject to stand still for 6 seconds. So we had to use an approach like the Relightables to construct these meshes relit by the novel lighting condition. And what we noticed was these were not as photorealistic compared to the baked-in lighting, which is understandable because there are certain approximations like a handcrafted BRDF, and the rendering has no subsurface scattering and no global illumination considerations. So how much do we lose? This is what we lose. We go from this mesh on the left with baked-in lighting to the relightable mesh on the right. And you can notice that it's quite uncanny compared to the mesh with the baked-in lighting. So what happens if we run looking good on this data? We did run it, and it looked fine for seen people. If you can notice here, the predictions on the left and the original input mesh on the second last column. It does fairly well. We were happy with this. But moving to unseen people, we started to notice further deteriorations. There was lower resolution. The mask started flickering more. And what we realized that generalization is just hard for an approach like a UNet with large receptive field, which is very prone to overfitting. Also, since our ground truth actually came from OLAT data sets like the target images, we did not have a lot of pose variation for an approach like looking good to generalize well. So we started thinking from the scratch. We wanted to come up with a different approach that would generalize better. And to recap the goals of this approach, we wanted to synthesize novel viewpoints, we wanted to synthesize novel lighting conditions, and we wanted to generalize to new motions, and unseen people. So over here, it's the general idea is shown once we have all this synthesized imagery. Of course, the end goal for us was to synthesize these composited images under any arbitrary HDRI environments with the correct background. And this would serve as ground truth to train a lot of these approaches for that were meant to generalize to in the wild conditions that we care about. So that's the end goal, compositing and using this composited relit data as ground truth for approaches that were meant to run in the wild. Now, how did we do this? Let's talk about the deep relightables pipeline, the new pipeline that we designed. So what we did was we took gradient images as input plus the view direction and fed it through a feature extractor, which was essentially a UNet. Now, these extracted features were then warped to UV space using pre-computed warps based on the geometry. Once they were in UV space, these were pooled together such that we are invariant to the number of incoming views, and we are invariant to the order of the incoming views. And we ran a bunch of one-by-one convolutions to get a neural texture. Now note that this neural texture is very different from the neural texture in approaches like deferred neural rendering because they are actually regressed from the input images. That means that they have the ability to generalize to new people and unseen poses, whereas deferred neural rendering would have to synthesize a texture per pose or per person. Now, this texture is then fed to the neural rendering module, which actually feeds in light-dependent input and the target viewpoint-dependent input, warps the neural texture to the target viewpoint, and finally re-renders it to get a rendering that was nearing photorealism, in our opinion. So let's look at a few features of the feature extractor. It takes gradient images as input. Now, the gradient images have a lot of information. They have albedo information, they have normals information, they have view-dependent effects information, because you can see the gradient images as this weird multiplexed image where every view direction corresponds to a different color. So these enable moving performers because we can alternate between the two gradient images while the person is moving. The view direction input to the feature extractor actually enables these features to reason about these view-dependent effects. Once the features have information about which view the gradient image corresponds to, it can correlate the colors coming from that view and reason about view-dependent effects based on the color of the reflections from all the directions. These features also had relatively large receptive field because it was a UNet-based feature extractor. And the interesting thing about that is it enables the features to reason about pixels that the geometry did not capture. Now note that when we do use this warp pre-computed using geometry, we lose all the pixels that the geometry did not capture. But since we are warping features, each feature had a receptive field that was larger than itself and can encode information about its local neighborhood. The actual regressed neural texture, the neural UV features, as I mentioned earlier, are regressed from the input images and thus support generalization to unseen people and poses, which an approach like deferred neural rendering could not be able to. Another cool thing is that it supports different resolutions at train and test time. What this means is that the resolution of the UV texture could essentially be something like 1024 during training to avoid memory overflow constraints. But could be increased during test time by changing the warps to actually warp into a higher resolution UV texture. And this is something we tried, and it actually gives better results during eval than training, which is kind of cool. The feature pooling enables feature extraction from a varying number of viewpoints and actually makes it invariant to the actual order of the viewpoints. In addition to this, we run a bunch of one-by-one convolutions. Some things to mention is that the pooling is actually a weighted sum. The weights for each feature coming from a different viewpoint are actually determined by the camera visibility of that viewpoint. What this means is that we weigh pixels that are front-facing higher, something that's commonly done in geometric reconstruction pipelines. As I mentioned, because we do a weighted sum, it's independent of the order of viewpoints, and it enables training with few views, but evaluating with all available views. Another cool thing is that we can actually run the feature extraction stage only once during eval for novel view synthesis, and accumulate all the views into this texture, and then run only the re-rendering module several times for each novel view. Another thing that is essential to making this approach work is that we support changing UV parameterization. The warps are pre-computed based on geometry, and the one-by-one convolutions do not see the spatial extent of the UV texture. That means if the position of pixels keeps changing in these warps frame to frame, the approach would still work. Now, the changing parameterization is actually something that's very common for moving performer dynamic capture, unless you're using something like a body model, which has its own shortcomings. It's likely that the parameterization might change. And so this was actually needed to enable generalization to moving performers and unseen poses. Looking at the neural re-renderer, or the neural renderer in this case rather, the UV features are warped to the target viewpoint, and then we add a bunch of light-dependent information, which we call the neural shading module, if you look at the top. Now, the light-dependent information is in the form of this light visibility map and this reflection map. Now, arguably, one could say is that we could just pass in the light direction vector, and that's sufficient information, and it is. But we noticed that we got better generalization and better results by converting that information into a light visibility and a reflection map, which were in the form of 2D images that made a lot more sense to a convolutional neural network. I'll talk about that in a little bit more detail in a bit. The second module was this alpha mask prediction module, and what we realized was for accurate compositing, we needed a good alpha mask. We used a simple UNet here to actually take the resampled features and the mask that comes from geometry and to refine it with a ground truth alpha mask, which was computed on the target images using more complicated alpha prediction methods. And we give this as input to the neural rendering module as well. Now, the neural rendering module takes all this information and synthesizes the final image, which is under a novel lighting condition, in our case, which is a one light at a time image. And once we have a basis of one light at a time images, we know that we can synthesize any arbitrary relit image from that and composite it into any HDRI background. So some cool things about the re-renderer is that, as I mentioned, the view direction input is the same as the feature extractor. It enables the network to reason about the view-dependent information that is present in the gradient images. The light visibility input improves the quality and generalization of self-occlusions, because this visibility map is actually factors in geometry, and self-occlusions would actually be present there. Similarly, the reflection map input improved the quality and generalization of view-dependent effects for us, and enabled us to synthesize view-dependent effects at the one-by-one convolution level. So something to mention is that this re-renderer actually first runs a bunch of one-by-one convolutions and synthesizes an RGB at the one-by-one conv level, and then goes into the UNet part of it, which has receptive field and is potentially more prone to overfitting. So the outputting the RGB at the one-by-one conv level also enabled us to improve generalization to unseen people, essentially, and unseen poses. As I mentioned, the alpha mask prediction enabled us high-quality compositing. And finally, one thing to mention is that we trained this with perceptual losses, but we found that fine-tuning it a bit with the adversarial losses improved results. Whereas if we started from scratch with adversarial losses, we had certain issues converging. And this is something we are still exploring. I guess this is because it's full body data, and the distribution of data is a lot more difficult than something like faces. So let's look at some results. Here are the view synthesis results of the deep relightable approach. As you can see, it's fairly temporally stable. All the high frequency lighting effects are present. It does fairly well, and I'll show a comparison with looking good and deferred neural rendering in a bit. Similarly, now if we add illumination synthesis to the viewpoint synthesis, you can see that the specularity is accurately generated, and over here you see 3 novel views with a bunch of novel lighting conditions with a single light circling around the person. Over here, we show that we actually work on people under motion. This is a fixed view, but 3 novel lighting conditions while the person's moving. And as you can see, the temporal stability is fairly good. The specularities are decent on the face as well as on the hair and the shiny regions. Now we show that we are doing everything jointly. So these are novel people, novel poses, while we synthesize new viewpoints, and we synthesize new lighting conditions. And note that this is the first neural rendering approach, to the best of our knowledge, that synthesizes novel viewpoints and novel lighting conditions while supporting people under motion and supporting generalization to unseen people. Quickly show what the alpha mask results bring us. It improves the mask coming from geometry and leads to better compositing, as I mentioned earlier. And here's a comparison of the view synthesis results with other approaches, looking good on the left and deferred neural rendering in the middle, and the proposed approach on the right. You can see that our view-dependent effects are very comparable to deferred neural rendering, with the added ability of being able to generalize to new motion and new people. And our approach does not have as many issues as looking good has, with mask, with temporal stability, given training data that has not seen a lot of pose variation. Quickly want to mention that we also ran a comparison with NERF, which is a new cool method, volumetric kind of based method, that we wanted to see whether it works or not in our approach. We were not able to get the same quality as we got with relightable textures with an approach like NERF, even when overfitting to a single person and a single lighting condition. And we're still playing around with this. It might be that the MLP did not have enough capacity to synthesize these high resolution outputs, which are close to 2K resolution. It might be some other things. We're still exploring this a bit on our end. Here's a comparison with deep reflectance fields. As you can see, that our approach actually produces better occlusions because we support because we input this light visibility map, which deep reflectance fields does not have. And thus generalization to new people tends to be better in terms of occlusions from our approach. And finally, we show a comparison of relightables on the left with deep relightables on the right, and show how much we gain by using neural rendering to do this synthesis of novel viewpoints and lighting conditions, and compositing on different backgrounds. The geometry on the hair is better, the actual boundaries are better, the alpha mask is better in the proposed approach. Here you can see it's fixing some more things. And so on. So quickly wanted to mention what we use this for again. We wanted to use this neural rendered composited data as ground truth data for training for tasks in the wild. So this provides us data augmentation via more viewpoints from viewpoint synthesis, more lighting conditions. Oops, that's time. And it enables us to have arbitrary backgrounds with alpha compositing. And of course, this is better than the state-of-the-art geometric pipelines like Relightable in terms of photorealism, in terms of the quality of the geometry, and also in terms of the quality of the actual maps that we use to composite. And quickly wanted to tease some in the wild applications that we're working on. Not a lot of details here, but we are working on relighting, we're working on light estimation, we're working on alpha matting, depth estimation, pose estimation, all of this in the wild. And we are using neural rendered data as ground truth for a lot of these things to enable generalization to multiple different people and scenarios and background and lighting conditions. Here on the top right, you see some of our latest work on shadow removal, which was published at SIGGRAPH earlier this year. And in the bottom left, you see some depth estimation from single viewpoints. And in the bottom right, you see deep light, which is environmental lighting estimation from arbitrary environmental images. With that, I'd like to thank you with this little teaser of what the proposed deep relightable approach or relightable textures approach is capable of.
Hi, my name is Steve Lombardi, and I work at Facebook Reality Labs, which is the VR and AR research arm of Facebook. And I'm going to talk about neural volumes, which is a method for representing, animating, and rendering moving people and objects. In this work, we create a method for taking multi-view video from a capture stage, ours looks like this one, and we create a volumetric model that can be rendered and animated. By animated, I mean we want to create new performances similar to the ones we've seen during training. The reason why we want to do this is because the goal of our lab in Pittsburgh is to take real-life face-to-face social interactions and bring them into VR. In order to do that, we built custom VR headsets with cameras inside to capture the face. Because these captures are inside the headset, they give this patchwork view of the face. So you probably wouldn't want to interact with a person just by looking at these images. What we'd like to do is somehow reconstruct a person's full face from those camera images and present it to another participant from their point of view. We propose to solve this problem by creating a codec. A codec consists of an encoder and a decoder, and their job is to compress and decompress data into a small representation called a code. The idea is similar to a video codec, but with an additional control of the viewpoint that we decode and render the face from. In this talk, I'll be describing a system to decode and render people and objects in real time controlled by a code vector. If you want to know about how the encoder system works, check out the paper VR Facial Animation via Multiview Image Translation. So a decodable avatar is important, but why volumetric rendering? Last year, we presented our work on decoding faces with the triangle mesh-based representation. This approach works well for the face, but not so much for interesting hairstyles, partly because of these hard silhouette boundaries. It's also limited to modeling objects that we have a predefined mesh and tracking algorithm for. In this example, the mesh cuts off above the shoulders because that was the extent of the mesh model and tracking algorithm we had. And if the person is wearing glasses or more elaborate clothing, we would need an explicit model and tracking algorithm for that as well. In this work, we're using a semi-transparent volume representation, so the rendered images can take on a softer appearance, which works well for hair. And because we're implicitly learning the geometry during training by learning the contents of the volume, we don't need a tracking algorithm to use this approach. The formulation of this method is basically a multi-view autoencoder. We take the images from the capture system and use them to compute a code vector Z. The code vector Z, which is a description of the scene, is input to a decoder that produces a volume containing RGB values and opacity values. The volume is rendered by integrating along rays in space. Finally, an L2 loss is placed on the rendered image compared to one of the views. One of our main contributions is creating decoders that can generate high-quality outputs while running in real time. So first, let's take a look at what the volume is and how the volume rendering works. We represent objects and scenes with a semi-transparent volume where each point in space has a color value and an opacity value. To render the volume, we use a volume ray marching procedure, starting from the camera center along the ray defined by each pixel. In this diagram, R0 is the camera center, RD is the ray direction, and R of t is a position along the ray. The ray marching procedure produces two images. One is an opacity image, which allows us to map the rendering with other objects, and the other is an RGB image. The idea is that for each pixel, you integrate opacity along that ray to generate the output opacity image, and integrate color times opacity along the ray to generate the color output image. There's only one problem with this formulation, and that's the integration is purely additive, so there's no way to model occlusions. We need to change this factor to enable occlusions. To do that, we introduce an auxiliary variable that is equal to the volume opacity value when the integrated opacity along the ray is less than 1, otherwise it's 0. It basically acts like a switch that stops integration once the opacity of the ray reaches 1. This allows the system to model both transparent and opaque surfaces. The process would look like this. On the left, you'll see the integration proceeding along the ray, and at the bottom, you'll see images forming. We can't really analytically evaluate this integral, so what we do instead is numerically integrate it. So now we take discrete steps along the ray. Alpha k is the output opacity at step k. This equation says, to compute opacity, we sum up the volume opacity at each point multiplied by the step size dt and clamp it if it goes above 1. Then to compute the color, ck, at each step, we sum the volume color at each point weighted by how much the image opacity changed from the last step. The PyTorch code for this is actually super simple. So we have two variables that we're trying to compute, the final opacity image and the final color image. In the first step, we sample the values of the volume at our current ray position using a sample function that I'll describe later. Then we compute the difference that tells us how much to contribute to the final values. Finally, we accumulate the sampled values into our images and update the ray position. The output opacity value is important since it allows us to matte different backgrounds. Notice how on the glasses the transparency is correctly estimated and you can see the background through them. So that's how the volume ray marching works. Next, I'll describe how we came up with volumetric decoders that produce high-quality real-time renderings. The volume decoder takes the code Z, which represents the state of the scene, for a face that would be the facial expression in pose, for example, and produces the semi-transparent volume. The way this works in the PyTorch code is that the decoder produces a dictionary of values depending on how we represent that volume, and the decoder has a function called sample that returns a sample from the volume at any point. A simple type of decoder is a uniform voxel grid decoder. To sample from this volume, we trilinearly interpolate the values at the sample points. In the paper, we experimented with 3 types of decoders, 2 that use convolutions to produce a uniform voxel grid with final sizes 128 cubed and 32 cubed, and a linear basis decoder with a final size of 128 cubed. These 3 architectures trade off speed and quality, as I'll show later in the results. This diagram shows the convolutional architecture we use to generate a 128 cubed voxel grid. It's a series of transposed convolutions at successively smaller channel sizes. The sampling function for this volume is just one line. We use PyTorch's grid sample function to do the trilinear interpolation. Don't worry about all this extra stuff, it's just to make sure the tensor shapes are correct. The decoder class is pretty simple too. We just create a bunch of transposed convolutions and then we run them. So if we try to actually use this decoder, the results aren't very great. We get a bunch of blocky artifacts because the voxel resolution is relatively low. So why not just increase the voxel resolution? If we wanted to double the resolution to 256 cubed, we would need to perform roughly 8 times more operations, and the 128 cubed convolutional decoder already runs at only 20 frames per second, so simply increasing the voxel resolution is infeasible. What would be better is if we can make more of the resolution we had, for example, by not modeling so many empty voxels, or shrinking voxels where there's lots of detail. To address this problem, we produced 2 volumes. One is a voxel grid containing the color and opacity, and the other is a warp field. Warp fields are useful for modeling motion, but they're actually even more useful in our case. So now to sample the volume, we first sample the warping volume and use the result to tell us where to sample the template volume. This allows the model to shrink voxels down to increase their effective resolution and minimize the amount of voxels used to model empty space, in addition to modeling scene motion. This gives us the benefit of producing uniform voxel grids with fast GPU convolutions while escaping the uniform grid structure artifacts. Importantly, no additional supervision is required for the warp field. It's trained only from the image reconstruction loss. The code for the sampling function for this decoder is only one additional line. The first line samples the warping volume, which tells us where to sample the template volume. Here I'm showing a rendering of a model using a warp field that produces a high-quality reconstruction without blocky artifacts. And on the right is the template volume rendered without the warp field. You can see that it's kind of increased the amount of voxels it uses to represent some areas, and it's factored out a ton of motion from the scene. Notice how the head is almost totally fixed on the right. Here's another example to show how the warping and template combination can increase effective resolution. The animation interpolates between the warped template and the unwarped template. You can see that it's actually utilizing more space to model the head. An easy way to produce this warping is by using 3D convolutions, but convolutions don't tend to naturally produce good warping volumes. A 3D convolution might be able to easily produce a 3D translation, but to output, for example, a proper 3D rotation is more difficult without direct supervision on the warp field, which we don't have. To address this, we create a spatially weighted mixture of affine warps inspired by linear blend skinning. The idea is that we decode a small set of affine warps, each having rotation, scaling, and translation, and a 3D spatial weighting that mixes those separate warps to generate a final 3D position. We define the warp field as a weighted combination of affine warps, where capital A is the application of the translation, scaling, and rotation to the point X, and the weight factor little a is sampled from the weighting volume after applying the affine warp. We compute the final warping volume for a 32 cubed voxel grid and sample it in the sampling function. So that's how the decoder works. So now let's take a quick look at how we produce the code value z. Note that this encoder is different than the one I talked about at the beginning, and its only purpose is to train the decoder and provide a good latent space. The encoder network takes 3 input images at a given time instant and produces an embedding of the scene. The 3 input views that we use are fixed across the entire sequence. Note that this doesn't mean that the model can only produce images near these views. The system is supervised using every viewpoint. The purpose of the 3 images is just to compute a representation of what's happening at that point in time. The encoder consists of 3 convolutional branches with final encodings concatenated together. We use a VAE-style encoder that produces a Gaussian distributed latent space that gives useful properties like smoothness and compactness to help us create novel animations. That's all I'll add about the encoder. Finally, let's talk briefly about some of the details of training the system. If we implement the system as I've described it, we end up with a lot of extra stuff in the reconstruction. This extra haze appears because the decoder learns to place very low opacity voxels in front of the object to help model view-dependent effects. Since it's very low opacity, it barely affects the reconstruction from the other views. To reduce these artifacts, we add 2 priors to the training loss. We place a beta prior on the final opacity map. The intuition is that most rays should either strike a fully opaque or fully transparent area. We also place a TVL1 prior on the log opacity values of the volume. The idea is that there tend to be sharp boundaries between empty space and objects. We place the prior on the log opacity instead of the opacity because it increases the sensitivity of the prior to small alpha values where the artifacts tend to occur. Let's take a look at some of the results from this system. This is one of my favorite examples. We took some hot water in a mug and dropped dry ice in it and captured the fog as it was pouring out. This example is a fuzzy toy that has these really long, thin hairs, and there's a lot of motion, which would make it a tough example for traditional tracking or reconstruction methods. Here's a capture we did of different people with different hairstyles to show how this approach works in general. We also have a larger capture system that we can use to capture a complete person, and we use data from that system to generate this reconstruction. Because we're modeling a larger area, the resolution isn't as great as when we're only modeling a head. I mentioned before that the system will try to model view-dependent effects by adding additional voxels, but we can actually try to model the view-dependent effects by telling the decoder where I'm looking at the object from. In this case, only the RGB is affected and not the alpha values. This is a bit of an extreme example, but you can see that the amount of extra stuff around the lamp has decreased, and the reconstruction looks better. The refraction and high-frequency specularities are a bit more than this view condition decoder can handle, so it may be interesting to try to incorporate this into the formulation directly. I also mentioned earlier that there are a few different decoders that we use. So far, I've shown results from the 128 cubed convolutional decoder because they generally look the best, but the model doesn't hit 90 Hz in VR. We have 2 alternate models that do. One is a convolutional decoder with size 32 cubed, and the other is a linear basis decoder with a size of 128 cubed. In general, the convolutional models are better at modeling scenes with more complex motion, but the linear basis decoder can get better detail. We mentioned that we want to animate these models, so I'll show 2 ways that we demonstrate this. The first is with latent space interpolation. We can pick 2 codes. In this example, I've picked a code representing a cheek puff expression and an angry expression, and linearly interpolate between them to create the in-between expression, which should look like we would expect my face to move. Here we show our ability to animate a model by adding an additional input to the decoder, in this case head pose, being controlled and indicated by the purple dot. You may have noticed that in some examples the resolution of the model seems low. This can happen if it's a complex sequence with a lot going on. To address this, we propose a hybrid rendering system that uses a deep appearance model for the face and a volumetric model for everything else. The way it works is that we render the volumetric model with ray marching, but if the ray hits the mesh, the algorithm terminates and we use the background matting equation to incorporate the mesh texture color. For the hybrid rendering decoder, we use the linear basis voxel decoder so that the entire system runs at 90 Hz. Here's an example of just using a mesh versus the hybrid rendering with mesh and volume. To wrap up, I wanted to touch on some of the limitations of this approach and talk about some potential future directions. First, as you saw, the approach has some artifacts. There are extraneous voxels reconstructed, and sometimes it can't get the resolution as high as we'd like. Some of these can be improved with the decoder innovations and maybe some additional priors. Some of the resolution issues have to do with the fact that the warping field doesn't model all object motion. The more the warp field models the motion, the more capacity the voxel decoder has to provide a higher resolution detail instead of spending that capacity modeling motion. The warping field modeling all motion also helps with latent space interpolation, although the inverse warps which we're using don't interpolate as well as forward warps do. Finally, voxel grids are inefficient. They waste data representing empty space. It's hard to take advantage of acceleration structures like sparse voxel aux trees, for example, because they're not really compatible with convolutions. One cool thing I think about this work is how general this framework is. One alternative to the stuff I presented is to actually get rid of the RGB portion of the volume and compute color by projecting the sample points back into the training images. You can no longer animate the model, but it does allow you to do pretty good novel view synthesis. Thanks very much.
Hello everyone, I'm Ohad Fried, a postdoc at Stanford University, and today I would like to talk to you about the open challenges in neural rendering and a bit about social applications. But first off, I would like to thank all my wonderful co-authors, some of which you've already met today, but there are many that you haven't. This tutorial was a true collaboration between great researchers from many institutions, which I am proud to call my collaborators. And I would also like to thank all the guest speakers that were kind enough to take the time today to teach us about their works. Okay, open challenges. At this point, I hope most of you are convinced that neural rendering has already impacted many important research directions in computer vision and computer graphics. But of course, we're only at the beginning of the journey. Neural rendering is still relatively new, and there are many open challenges and existing opportunities for future research. There are many open challenges, as I said, and today I would like to emphasize three of them. First one is generalization, or rather the lack of generalization. Then there's editability, so how can we make neural rendering useful for users interacting with the system? And also multimodal representations. So that's moving beyond pixels and photos and videos to other modalities. Let's go over these one by one. Okay, so what do I mean when I say generalization? Here's a system that uses neural rendering to convert text transcripts into a video of a person saying the transcript. You type in the text, and this is what you get.
Okay. The market closed today with Apple's stock price at $182.25 per share.
Now, while the results are quite impressive, it is important to understand that this system is extremely specific in its training and applicability. The neural renderer's task, in this case, is to convert frames that include CG renderings and missing parts into photorealistic frames. The network is trained for this specific person with this specific clothes, hairstyle, and backdrop, and will completely break for a different person. So one immediate question is why, right? What's the advantage of being this specific? And the short answer is that result quality is higher since we ask the network to learn a much more constrained distribution. However, there's also a huge disadvantage. For each new video, we need to retrain a neural network, which requires data and costs time and storage. And that's what I mean when I say generalization. It's the ability to work on varied inputs. I kind of picked on one example, but when you examine the state of the art, we actually see that specifically for reenactment tasks, most methods do not have this generality property. Here I'm showing you part of our Your Graphics state-of-the-art report, which this tutorial is based on. This is part of a table that summarizes the different properties of the methods we surveyed. And as you can see, the generality column is very much in the red for reenactment methods. Okay, so I talked about generalization, but generalization over what? As always, it really depends on the problem you're trying to solve. Going back to the example we've already seen, we would really like it and all applications that involve humans to work not just for a specific person, but for all people. And of course, it's important to remember that people are extremely diverse in properties such as age, gender, physicality, can also appear in strikingly different poses, clothes, makeup, etc. But of course, people are not the only object class in the universe. We have various algorithms that are pretty robust when they see cats and chairs, just because we have large data sets for cats and chairs. But what we really want is algorithms that can handle arbitrary objects, even if we don't have lots of data for such objects, and perhaps also handle objects that we never saw before. Going beyond individual objects, some neural rendering tasks can benefit from generalization over different environments and for making them applicable to large scenes with many objects and object types. Essentially, what we want is a neural rendering algorithms that can be trained once and then used everywhere. Now, one might be tempted to think that given enough data, generalization will spontaneously emerge. However, we are starting to see evidence to the contrary. and you saw some evidence to that during this tutorial. A network architecture might not be able to generalize, not due to the lack of data, but due to the architecture itself. And thus we believe that there are many interesting opportunities in bringing in classical computer graphics knowledge into the design of these architectures to make them more general and to allow both interpolation and extrapolation to unseen data. Okay, the second open challenge I want to talk about today is editability. Traditional computer graphics systems are extremely controllable. For example, when modeling and rendering, an artist can explicitly specify every object in the scene, every light source, texture, material, camera, everything. When we create animations, every joint can be controlled. When moving to neural rendering, many of these human understandable elements might disappear. Now, for example, instead of meshes, you might be dealing with an abstract parameter space. And it is much trickier to introduce meaningful control knobs to an abstract space. There are a few ways one can go about introducing controllability. All have been tried to various degrees, but all can definitely be further explored. First off, don't learn everything. Right? It might be beneficial to move away from a completely learned, completely opaque system to a hybrid system in which some parts are learned and some are fixed. And in such a hybrid system, the fixed human interpretable pieces can be used to add the controllability. Second strategy to introduce controllability is by learning an abstract space and then assigning meaning and controllability to it in retrospect. What do I mean by that? So using a few labeled examples, you can do that. For example, in an abstract space that represents faces, we can search for and find a gradient direction that adds or removes smiles, as an example. Lastly, control can be baked into the network architecture and training procedure. So if a neural rendering system is trained in such a way that some of the inputs are human interpretable, those can be used in inference time to introduce meaningful controllability. Just to drive the point home, there are many pieces that can be learned, and we need to make informed decisions. In classical rendering, all these elements, geometry, materials, cameras, lighting, textures, others, they all take part in the rendering process, and all of these can be learned from data in some form or another. So the interesting question to me is, for a given application, which ones should we learn? And as I said before, how do we combine these fixed and learned representations to help the network generalize and introduce controllability? Okay. The last open challenge I want to briefly mention today is multimodal neural scene representation. While rendering is usually about creating pixels, photos, and videos, when using neural rendering, we have an opportunity to learn a much more holistic representation of scenes, which includes visuals, but also other sensory input, like audio, touch, smell, and even elements beyond our senses, such as hyperspectral imaging. Trying to learn a multimodal representation obviously comes with its own set of issues, which we need to develop new architectures and datasets to handle. However, it also holds a great promise, right? Applications such as VR can benefit from this quote-unquote rendering framework that can render all elements of the scene, not just pixels, creating a really immersive experience that includes visuals, sounds, haptics, etc. Okay, before I conclude, I would like to briefly mention the social implications of neural rendering. I'm a great believer that we must be extremely mindful to the broader impact of our research on society. And specifically for neural rendering, while many of the methods that we saw today are mostly irreproachable, some of them, especially those that are related to human synthesis or synthesis of human beings, have legitimate and extremely useful use cases, but can also be used in a nefarious manner, right? Something like fake news comes to mind. Now, don't get me wrong, I'm not trying to say that synthesis of photorealistic scenes is new. It's obviously not new. We've been doing it for years, for example, in the movie industry. What is new is the approaches are making the synthesis easier and available for more people. So if we're not careful, this might lead to a world in which social media is swamped with fake images and videos, overwhelming media consumers and making it pretty much impossible to gain trustworthy information. And thus, we propose a few best practices. First of all, synthesized content should be clearly presented as synthetic. This might be obvious from the context or by using an embedded label or informative descriptions. Also, whenever a human is being synthesized, artists should obtain permission both from the content owner and also from the person which is being synthesized. We also believe that forensic efforts are extremely important, and indeed we are involved in forensic research to detect synthetic content and verify authentic media, including a workshop here at CVPR. Many mitigations are not technological, but instead have to do with law and policy making, and we should all take part in such discussions to make them more useful and grounded in current technological ability. And lastly, I would urge each and every one of you, when relevant, to explicitly address social implications of your research. I'm not sure we do that enough as a community, and this can be a section in your paper, a blog post, any other method that will help explain why the research is pursued and guide its applications in a direction that you believe to be a good one. Okay, let's do a short recap of what you've heard today. We talked about the definition of neural rendering and the importance of controllability in that definition. We saw representative applications from 5 different categories: semantic photosynthesis, novel view synthesis, free viewpoint video, relighting, and facial and body reenactment. And of course, there are many open challenges, of which we talked about generalization, editability, and multimodal representations. We truly believe, and hopefully managed to somewhat convince you today, that neural rendering has the potential to impact numerous challenges in both computer vision and computer graphics. And with that, I would like to thank everyone for listening, for being with us this day in this tutorial. If you're interested in a follow-up discussion, most of the presenters made themselves available for more questions, so please go to the tutorial website, neuralrender.com. There are more details there on how to join the conversation. And that's it, I guess. Thank you again. Have a great day and a great conference.